Okay, last time we started considering our 5-transistor differential amplifier, which was made from taking an MOS differential pair, like so, and putting on top of the drains of the two diff pair transistors a simple PMOS current mirror. And we thought about how this would behave in response to, say, a change in one of the inputs relative to the other one, which would be corresponding to sort of a differential mode change. If you recall, we had this notion that we had this output current I out, and we thought about holding the output voltage fixed with a voltage source. V out, and then thinking about what would happen if we let go. So let's assume we have VCM and VCM. We've got these currents here, I1, I2, I3, and I4. You remember we said that in this condition, with VCM on both these two inputs, the two currents, I1 and I2, would be equal to IB over 2. We would have the current mirror mirroring IB over 2 from the I1 side over to the I2 side here, and dumping that IB over 2 on top of the IB over 2 here, leaving I out equal to 0. And if we were to let go, the output would not move, because there's no output current to charge or discharge the output capacitance. But if we were to put in let's say a delta V1 here into the V1 side, well, that would steer a little bit more of the bias current over toward the I1 side. So I1 would be over IB over 2, I2 would be less than IB over 2. And so we would have our delta I1, if you like. We'd have a plus delta I1 here, and we would have a minus delta I1 here, and I out would be equal to 2 delta I1, because we've increased I4 by delta I1. So there's a delta I1 here, and there's a minus delta I1 here, and so I out is changing by 2 delta I1. Well, in that case, if we were to let go, then depending on whether delta I1 was positive or negative, the output would have to move up or down. And the only way for the currents to equilibrate would be for one of these two transistors to move out of the saturation region and into its ohmic region. And that would allow V out to stop at some place. And so we also thought about the idea that in the balanced condition, any output voltage within the range of voltages that would saturate both M1 and M2 would be sufficient to allow KCL to be satisfied, and so would be compatible with being a point on the voltage transfer characteristic. And that suggested that the voltage transfer characteristic was vertical at the place where V1 equals V2 equals VCM. So we want to go back and back to the balance condition here. So I'm going to take out the little delta I1s. And I out would be 0 in this balance condition. This pen needs a little rest. And so again, we have this notion that basically I out is 0, and if we were to let go of V out would not change. And so basically any output voltage would be consistent as long as M4 and M2 are saturated with this balanced condition. I want to think about what would happen if I were to put a delta VCM into both sides of this diff pair. Well, if I were to put a delta VCM on both sides of this diff pair, I will move this common source node voltage up by a little bit, delta V. We talked about these two transistors, M1 and M2. If we have a pure common mode signal, M1 and M2 are effectively in parallel with each other, and so behave as a single transistor whose strength ratio would be twice that of either one of them, and so V would move up like a source follower would. But if the early effect is negligible, like we've been assuming, then that wouldn't change the bias current. It wouldn't change the split of the bias current here between M1 and M2. They would still be IB over 2. Wouldn't change at all the amount of current being mirrored by the current mirror. And so I out would still be 0. And so if we were to let go of V out, there would be no incentive for V out to move. It would just stay put. And so that suggests that in this kind of idealized picture of the world, what we would call the common mode gain, ACM, which is effectively delta V out over delta VCM, would be basically 0. So we had also the notion that the differential mode gain from last time, which would be delta V out divided by delta VDM, these are actually partial derivatives of basically a voltage transfer characteristic, sweeping one of these around the other one, or sweeping a pure differential mode input, which would be actually, strictly speaking, putting a VDM in here and a minus VDM in here, or something like that, or plus half of VDM here, minus half of VDM there. But for sufficiently small finite deltas, the ratio of this will, in the limit, become that partial derivative. Well, in the absence of an early effect, this differential mode gain is basically infinite. No matter how small the delta V1 that we put in here, that would give rise to a change in the currents. And if these are really current source-like, that will result in a finite change in the output voltage. And if we take the limit as that delta V1, let's say, goes to 0, or the delta VDM goes to 0, you have a finite divided by an infinitesimal, and that limit is going to approach infinity. So here we have a situation where a circuit ideally would have no response to a common mode input, and basically a very, very large response to a differential mode input. And so that's the kind of behavior that we would like to see out of a differential amplifier, something that selectively amplifies differential changes and selectively rejects common mode inputs. Now obviously this is an idealization, and this isn't a realistic picture of what's actually going on. And so we'd like to develop a more realistic picture of what's going on. And in order to do that, we're going to need to take into account the early effect, because that's in effect what's going to be limiting the gain of this kind of circuit. So we're going to start on that project by thinking about how the early effect comes into play in the common mode gain of the circuit. Okay, so we're going to take the circuit apart and consider how the early effect comes into play for the current mirror, the PMOS current mirror, and for the differential pair. So let's think about the differential pair first. So here's the diff pair. Bias transistor, it's not MB, it's VB. This is MB. Bias current IB, I1, I2, M1, M2, V, and we're going to assume that we have a common mode, pure common mode input, VCM on both sides, and we have basically the output voltage here, and we're going to call this internal node here V3. Now, we're going to assume that these transistors are matched, but now they have a finite early effect. So we're assuming M1 and M2 are matched. And same temp. But VA is less than infinity. Well, if these two transistors are matched, and they have the same gate voltage and the same source voltage, then they'll be operating on the same drain characteristic. So M1 and M2 operate on the same drain characteristic. And so if I were to draw that sort of common drain characteristic here, maybe as a function of, we have I1 and I2 as a function of, let's say, V3 or V out. There'll be some voltage here, V will be somewhere, and we would have something like an ohmic region coming up from V, and then there would be some slope up here, so that there'd be some RO, 1 over RO1, 1 over RO2, and we would have either I1 or I2 over here on the right hand side. And so if they're on the same drain curve, and the drain curve is shaped like this, where there's some positive slope here, whichever of V3 or V out is higher, that will make I1 or I2 higher. So we would be able to say, if, say, V3 is greater than V out, we would have I1 greater than I2. Right, because we'd have more voltage across M1 than we have across M2, and so M1 would be operating further into saturation and would have a higher current than M2. If V3 equals V out, well, that would imply that I1 is equal to I2. That's the only place where the two currents will be exactly the same given a finite early effect. And if V3 is less than V out, that would imply that I1 is less than I2, because then M1 would be operating further down toward the ohmic region than M2. M2 would be higher up in saturation. Okay? So that's basically how the diff pair is going to, how the early effect is going to come into play for M1 and M2 in the diff pair. But what about the current mirror? Here's our PMOS current mirror. So you have M3 and M4. V out, I4, I3, and V3 here. This is VDD. We're going to assume again here that the transistors are matched, that they have a finite early effect. Okay, so we're going to assume M3 and M4 are matched, and same temp, but VA is less than infinity. Well, here again we have the situation where they have the same source voltage and the same gate voltage, and so they're going to be operating on the same drain characteristic as well. Right? So M3 and M4 operate in the same drain. And so if I were to plot their drain characteristic, it would be a PMOS drain characteristic. Right? So we know what those look like from lab 5. So we have I3 and I4 as a function again of, let's say, V3 and V out. And up here we have VDD somewhere. And these drain characteristics are deep in the ohmic region up at VDD, and they'll come up like this and be shaped more like that. So there'll be some slope here, which is going to be basically 1 over RO4, 1 over RO3. Or I guess I should say it's going to be minus 1 over RO. That's probably better. Minus 1 over RO3 or minus 1 over RO4. So RO is typically considered to be a positive parameter, but the way that we're sort of referencing V3 and V out, the slope is negative. Okay? So in this case, we have a somewhat different situation because of that negative slope, right? So in this case, if we think about V3 being more than V out, well, if V3 is higher than V out, that means that M3 has less voltage across it than M4, and so M3 will be closer to the ohmic region than M4. M3 might be over here somewhere, and M4 might be down here somewhere, and so M4 is going to have a larger current. So we're going to have here, if V3 is higher than V out, we're going to have that I3 is going to be less than I4. See, it's the opposite inequality here. And if V3 equals V out, I3 will equal I4. Again, they'll be at the same exact drain to source voltage, so they'll have the same gate voltage, the same source voltage, the same bulk voltage, and the same drain voltage, and so at that point their currents will be exactly equal even if we do have a finite early effect. And if we have V3 less than V out, well then M3 is going to be operating further into saturation because it has more voltage across it than M4. And so we have here I3 is going to be greater than I4. Again, we have the opposite sense of the inequality here in the case where we have V3 less than V out. And so we can combine these things. Right, so when we put these two circuits together and we think about the fact that there's no other place for current to go here at node V3. So KCL implies that in the steady state, I1 has to equal I3. So KCL at V3 implies that I1 has to equal I3. And so we can combine these inequalities by noting that we have I1 here, and we have I3 here, and those are equal. And so we can combine these things and say, look at the three cases. If, let's say, V1, or rather V3, is greater than V out, then we have I2 is less than I1. Okay, that's just flipping this around. And that's equal to I3, which is in turn less than I4. Right? So that implies that I2 will be less than I4. But I out, so KCL, if you recall from last time at V out, implied that I4, rather I out, was equal to I4 minus I2. And so we can subtract I2 from both sides of this inequality and find that I out, which is equal to I4 minus I2, is going to be, so this implied that I4 minus I2 is going to be greater than 0. If V3 equals V out, well, we have I2 equals I1 equals I3 equals I4. And so that implies that I2 equals I4 and I out, which is equal to I4 minus I2, is equal to 0 amps. If V3 is less than V out, the last case, we have I2 is greater than I1, which equals I3, which is in turn greater than I4. So we have that I2 is greater than I4, which means that I out is going to be, again, I4 minus I2, which is going to be less than 0. So we have here, combining these things, basically if V3 is greater than V out, then we have I out is greater than 0. It's positive. If V3 equals V out, I out equals 0. And if V3 is less than V out, then I out is less than 0. It's negative. All right, so what does this mean? This means that V out, if we were to imagine taking our circuit and putting it back together again, so that we have our VCM, VCM, VB, we attach a voltage source here. And we think about, letting go and seeing where it's going to move. If V out is less than V3, we figured out that I out will be positive, right? The current will be coming out of the amplifier. So if V out is below V3, the current's going to flow out. And if we let go, well, that current has no place to go other than our friendly parasitic output capacitance. And that I out is going to charge this capacitor. That's going to lead to a positive dV dt, dV out dt, and V out is going to rise. And it's going to rise until I out is equal to 0. Well, where is I out going to be equal to 0? I out's going to be equal to 0 where V3 is exactly equal to I out. Rather, V out. So V out is going to basically rise until it balances the voltage that is on the input of the current mirror. Right? So if we imagine the situation where, let's say, V out is higher than V3, well, we would have current flowing in. Right, we said I out is negative, so current's going to flow in. And if we let go, V out is going to decrease. That capacitance is going to be discharged, and it's going to fall until it's equal to V3. And so the only place where it's not going to move when we let go is if we start out V out exactly equal to V3. So that's going to be where the circuit actually wants to operate. So in a realistic situation, when we have matching but a finite early effect, there will be a point on the voltage transfer curve where V1 equals V2, where V out is going to be basically at the same point as V3. It's going to be about a diode drop below VDD. Okay? We do want to get actually a more quantitative handle on what is the common mode gain of this circuit. And we're going to use this notion that V out basically does, in the pure common mode case, okay, please don't get confused into thinking that that this idea that V out is always equal to V3, that's only true for this balanced configuration where V1 is equal to V2 equals a pure common mode input signal. That's the only time. So when V1 equals V2 equals some common mode, then V out will be equal to V3. Okay, that's what we've figured out with a finite early effect. We're going to use this notion to figure out what is the common mode gain. So what is ACM for the circuit? Well, what we're going to do is figure it out piecewise. We're going to say, okay, what happens when we put a delta VCM into both sides here? Well, we said before that in the common mode, M1 and M2 are effectively in parallel, and this diff pair acts pretty much like a source follower. And so we know something about what the common source node will do. We'll say the common source node is going to have to increase by some delta V, and we can actually write down how delta V relates to delta VCM. Delta V is going to be kappa times delta VCM, because it's like a source follower, and the incremental gain of the source follower is kappa. Well, so here we have IB over 2. Let's call this maybe I1, I2. Well, what happens to the current flowing through MB if its drain voltage increases by delta V? Well, we always assume that MB is saturated, and so in the absence of an early effect, the current would remain the same and nothing would change. Okay, but that's not very interesting or realistic. That would lead us to the conclusion that the common mode gain is 0. And we know it's not going to be exactly 0. And so we have to take into account the early effect on transistor MB. Well, there's going to be a delta IB, an increase in the bias current due to the increase in the drain to source voltage. And that delta IB is going to be equal to the delta V, the change in the drain voltage, divided by the slope of the drain characteristic, which is ROB. Or times the slope, actually. The slope is 1 over ROB. And so we can substitute this in here and write this as kappa times delta VCM over ROB. Well, what happens to this increase in IB? Well, we're going to have that, since the two transistors in the diff pair are splitting the bias current 50-50, I1 and I2 will also have to split that increase in IB 50-50. And so we're going to get a plus delta IB over 2 increase here, and a plus delta IB over 2 increase there. And so delta I1 is going to equal delta I2 is going to equal 1/2 of delta IB. And so that's going to have to be equal to kappa over 2 times delta VCM over ROB. Well, we're going to have the same increase in I3 and I4 as we had in I1 and I2. And so delta I3 equals delta I4 equals kappa over 2 times delta VCM over ROB. And now we have to ask, well, how is V3 going to have to change in order to allow more current to flow in it? Well, it's a PMOS transistor, and so in order for it to pass more current, the gate voltage is going to have to decrease. And so V3 is going to have to go down, so it'll be a delta V3 and a delta V out, since V out is mirroring what's happening on V3. We're going to have a delta V out equal to a delta V3, which is going to be minus, right, because it's got to go down. And we have to figure out what is that delta V3? Well, we have here a change in the gate voltage accounting for an increase in the channel current. And the parameter of the transistor, the incremental parameter of a transistor that tells me how much additional current do I get for a given change in the gate voltage is the transconductance gain, right? And so V equals I over R. I is equal to G times V. And so a change in the current, to get a change in voltage by a change in the current, we're going to have to divide by the transconductance gain. And so it's going to be minus delta I3 over GM3. And so that's going to be equal to, we substitute in how I3, delta I3 relates to our input, we're going to have our answer. So it's going to be minus kappa over 2 times delta VCM over GM3 ROB. And so ACM, which is delta V out over delta VCM, is going to be equal to minus kappa over 2 times 1 over GM3 times ROB. Now, what kind of number is this? We have here something that's negative. Okay, so it's a negative number. So an increase in the common mode gain, or an increase in the common mode, will result in a decrease in V out. Kappa is a number that's on the order of somewhere in the range of 1/2 to 1, and so kappa over 2 is going to be something in the range of 1/4 to 1/2. Okay, that's on the order of unity, or so. But what's this GM3 times ROB? Okay, now it's the GM of this PMOS transistor times the incremental output resistance of this NMOS bias transistor. And because the current levels are all tied together through KCL, basically, the bias current here determines what the current level is flowing in all the transistors. These parameters are going to be tied together in a way that's fairly similar to the way an intrinsic gain of a single transistor would behave. And so GM3 times ROB is going to be something like on the order of the intrinsic gain of one of these transistors, given the level of inversion that we're operating at. And so we have a number here that's going to be something like 1 over 100, or maybe 1 over a few hundred, or maybe 1 over many tens, depending on whether we're up in strong inversion or in moderate inversion or weak inversion. But this is going to be something like 1 over GSRO, 1 over the intrinsic gain of a transistor, which might be .01 or 0.001, something like that. So we would expect that the circuit will have a slightly negative common mode gain that's on the order of maybe 10 millivolts per volt, or maybe 1 millivolt per volt. We'd also like to get a handle on the differential mode gain and how that compares to the common mode gain. But that'll have to wait till the next segment, or maybe even the segment after that. That's going to be it for this one.